Hello and welcome to the screencast of the code that I have developed in the project End-to-End Reconfigurable IoT Stack, Best Practices for Large-Scale Deployments. This screencast aims to cover all the functionalities that I have created during the project. I shall start with introducing the libraries that I have used during the development of the Python script. The OS library, otherwise known as the operating system library, allows you to interface with the underlying operating system that the Python is currently running on. The CV2 library is used in the classification and labeling of objects. The NumPy library supports large multi-dimensional arrays and matrices, as well as mathematical functions that operate on the arrays. The PyCamera array is later used to produce a three-dimensional RGB array from the PyCamera's capture. This output class can be used to easily obtain a three-dimensional NumPy array organized as rows, columns, then colors from an unencoded RGB capture. The PyCamera module provides a Python interface to the Raspberry Pi's camera module. TensorFlow is a free and open source software library for data flow and is used in deep learning tasks. The system module allows us to specify the search path for modules. The time module is used to handle time. The GrowthPy module allows us to collect the available light present from the light sensor that connects to the GrowthPy. The GrowthPy subsequently connects to the Raspberry Pi 4 via its GPIO pins. To find out a bit more information about how to connect the light sensor to the GrowthPy, please go to the following link. The PAHO MQTT client module allows us to create a client class that enables the connection to an MQTT broker, which in this case is the cloud platform ThingsBoard. It also provides straightforward helper functions when publishing messages to the MQTT server. Finally, the JSON module is required to convert a dictionary data structure to a JSON object, which is the format requirement for ThingsBoard. We also import two Python scripts that are used in conjunction with the MS Coco dataset and TensorFlow's object detection API. The label map util uses numbers that are associated with objects from the MS Coco dataset, and this script helps to map the integer numbers to that object's names. The visualization utils improves the format of the displayed information, whilst the PyCamera is capturing and detecting objects for classification. So firstly, we set up the camera constants, and this can be modified depending on the resolution requirements. Models that have been pre-trained on the MS Coco datasets are used in this project and are found and downloaded at TensorFlow's Model Zoo. In order to download one of these models, just click on the link. To change the module in use, change the variable model name. Over here, we're able to grab the path of the currently working directory. Here, we get the path of the frozen interface graph.pb file in the directory of the neural network model that is currently in use. This contains the model used for object detection. In the path to labels variable, this is equated to the list of integers that are mapped to the name of the objects in the MS Coco dataset. The MS Coco label map.pbtxt contains all the objects and their unique ID. As you can see, the ID 1 equates to a person, ID 2 equates to a bicycle, and ID 3 equates to a car, and so on. There are 91 classes of objects in MS Coco. Label maps map indices to category names so that when the convolution network predicts 5, we know that this corresponds to an aeroplane. I have used TensorFlow's internal utility functions to carry this out. So primarily here, this loads the MS-COCO label map.pbtxt and validates it and equates it to the label map variable. Here, the label map is converted to the categories that it's related to, and then finally a category index is created that maps the integers to the category that is created. Next, we load the TensorFlow model into memory. The graph is the core concept of TensorFlow to present computation. We firstly create a computation graph and then pass the graph to TensorFlow. Although we only have one graph being used, it is still good practice to use the as_default bracket function. Then the serialized graph is imported into the current default graph. The session object encapsulates the environment in which operation objects are executed and TensorFlow objects can then be evaluated. Tensors are multidimensional arrays with a uniform type. So here we define the input and output tensors, for example the data for the object detection classifier. The input tensor is the image, and the output tensors are the detection boxes, scores, and classes, and each box represents a part of the image where a particular object was detected. Each score represents level of confidence for each of the objects, and the score is shown on the result image together with the class label. We also find out the number of objects that have been detected in a particular capture. Over here, the frame rate calculation is initialized. We use the cv2.getTick frequency, which returns the frequency of clock cycles. Also, the font for the output of the information stored is initialized here, and font Hershey Simplex is a handwriting type font, which is easy to view. The next part of the code is the MQTT configuration setup. We use a number of helper functions that makes MQTT straightforward to use. Throughout the client parameter is a unique client ID string, and the user data is user-defined data of any type that is passed as the user data parameter to callbacks. Primarily, the onLog function is called when the client has log information and is defined to allow for debugging. The level variable gives the severity of the message and will be one of MQTT log info, MQTT log notice, MQTT log warning, MQTT log error, MQTT log debug. The message itself is stored in the variable buff. The next function is the onConnect function, and this is the callback for when the client receives a CONNAC response from the server. The RC variable is the connection result. So if the RC result is a 0, this means that the connection is successful. If it's a 1, it's refused as a result of incorrect protocol. If it's a 2, there's invalid client identifier. If it's a 3, that means server is unavailable. If it's a 4, then it's a bad username or password. And it's a 5, that means unauthorized. If the connection is successful, the connect flag is toggled to be true from being false. And then a message is printed to the terminal saying connected OK. The onDisconnect function ensures that the client has disconnected successfully. The onPublish function is called when a message that was to be sent using the publish call has completed transmission to the broker. The callback is important because even if the publish call returns successful, It does not mean that the message has been sent. The mid variable is the message ID for the publish request. The mid value can be used to track the publish request by checking against the mid argument in the on_publish callback. Over here, we create a new instance of the client class called Python1. We bind the connect function to the client and do the same to the onDisconnect and onPublish functions. We then define the broker, which in this case is demo.thingsboard.io, which is our Thingsboard cloud platform, the port used, and the topic, which all stay the same. The next thing that must be changed is the username, because this relates to the access token that is directly related to the device that is currently being used in Thingsboard. So if you go to Thingsboard, then you click on devices, you click on plus to add a new device, and over here we can create a new device. Once we create a new device, we'll be able to copy the access token, and then we'll be able to paste it over here. We now connect to the broker using the connect function with the broker and port as the parameters. It is important that the script does not proceed until the connection has been established. Thus, time.sleep is used to wait and give the connection the time that is required. Later in the screencast, I will show how the data collected successfully published to Thingsboard. The next feature allows the user to choose which object they would like to classify, which may be required for different object detection objectives. This allows the script to be dynamic in nature. Although the MS Coco dataset contains 91 clusters of objects, it was decided that bicycles, road vehicles, including cars, trucks, and buses, and mobile phones would be detected. Each object in MS Coco has a number that is related to it, which is used in the script. For example, bicycle is 2, car is 3, truck is 8, bus is 6, and cell phone is 77. The number input from the user when the program starts is then equated to these numbers. The next part of the code is used to initialize the use of the Pi camera. The Pi RGB array is a custom output class that can be used to easily obtain a three-dimensional NumPy array, which is organized as rows, columns, and colors from an unencoded RGB capture. Truncate 0 allows us to reuse the output to produce multiple arrays by emptying the raw capture variable between captures. We use camera.capture_continuous to continuously capture images from the camera as an infinite iterator in a BGR format using the Raspberry Pi's video port. The CV2.getTickCount returns the number of clock cycles after a reference event. So we call this before detection and then after detection to get the number of clock cycles used to execute the function. We then acquire each frame and expand frame dimensions to have shape. A single column array where each item in the column has the pixel RGB value. The CV2.CVT_color converts the captured BGR image to GBR. We then perform the actual detection by running the module with the image as input. The Python script uses a two-dimensional 10 by 10 matrix to store the integers that relates to the objects that have been detected. This matrix is stored in the variable classes. The probability scores of each object that has been detected is stored in the variable scores, which is also a two-dimensional 10 by 10 matrix. During detection, the object integer values with the highest probability score automatically shifts to the first element of the first row of the matrix. We therefore use an if statement to check if the object we have chosen to detect equates to the class's 00 value. So if that value equates to each other, then the light sensor will be red. So the light sensor equals 0 because the light sensor was inserted into the number 0 port of the Grow Pi. And then the light sensor value variable now contains the light sensor readings. The OSPopen function was used to equate the output of each of the resource monitoring stats to a variable. I was then able to manipulate each of the outputs to ensure that only the information that I required was stored. So I used the VCGENCMD measure temp to investigate the temperature, the free -m to investigate the RAM used, the uptime to investigate the CPU load, and the MP stat to investigate the CPU usage. All data is then stored in a dictionary, which is named Resource Monitoring Agent. I then did a for loop through each of the categories, which contains the mapping of the integer values that relates to the object's names, to find the name of the object that relates to the number that was initially input into the system. We then create a final dictionary with all the information that needs to be sent to ThingsBoard via the MQTT communication protocol, and then convert this to a JSON object, which is the requirement. We then use this function, which helps to visualize the results. And the mp.squeeze function is used to remove single dimensional entries from the shape of an array. The boxes represent a part of the image where the object was detected. The scores is a probability score that each neural network model classifies the object. And the class is the class of the object that has been detected. Also, interestingly, we can change the minimum score threshold so that only objects that are detected with a certain level of probability score will be classified. The cv2.putText function is used where the frame is the image, the text to be drawn onto the image is the frames per second. The coordinates of the bottom left corner of the text string in the image is 3050. The font is font Hershey Simplex, which was already discussed earlier, and the color is RGB 25250 with the line type line AA. The cv2.imshow function provides the name of the window and the video captured by the Pi camera with the detection results. To calculate the frame rate at the end of detection, we calculate the tick count for the execution time after detection and equate this to the variable T2. We do T2 minus T1 for the execution time before detection, divide by the tick frequency Then we do 1 minus that figure for the frame rate. The program waits 1 second for the letter Q to be pressed to quit the program. We also make sure that the raw capture is completely empty so that another frame can be captured. And then finally, we do a camera.close function, which is important on the PyCamera object to clean up all the resources. Thank you very much for watching the screencast of the code of my project.